Welcome to lecture 9, and this is the first segment of this lecture. In this lecture we'll be using the theory of residues to compute the definite real Riemann integrals for certain types of the functions. So let's start with the first type of the integrals. So this is the trigonometric integral. So let's start, put it like this, type 1. And we write it down, trigonometric integral. And this is the integral of, that looks like this. This is from 0 to 2 pi. And here we have a function of two variables. And I substitute cosine t for the first variable, sine of t for the second variable, dt. So this is cosine sine t dt, where r, x, and y is a rational function, function of two variables. And without singularities, so maybe let's say which is well defined. Maybe write it down, which is well defined on the unit circle, and we will denote it. It's kind of an circle C, which is equal the set of all, you should remember, that's exactly Z. This is X and Y, satisfying the condition that X squared plus Y squared is equal to 1. So exactly that's the unit circle. That's the same circle that we have seen before. And that means we have here that one. So how the method works, so the integration, the method, put it like this, method, and we just simply do the following. We will derive the formula for the computations of these integrals, and this formula will be related to the following substitution. Notice that the circle, this particular circle, has the parametrization, maybe use the red color, parametrization zt is equal to EIT. So we may in certain way understand that my variable here z is written like this, z is equal e to the it, so this will be EIT. So that one is equal cosine t, and that one is plus I sine of t. And now z minus 1, which will be E minus IT, will be equal to the cosine of t minus I sine of t. And now what we can do, we can check out two possibilities. What is this one? If I put here z plus z minus, I will be getting from these two equations that this is equal to cosine of t. On the other hand, z minus, we are getting this is 2i sine of t, and consequently we have here that I can substitute, I can reformulate the integral I as the integral of a complex function, of a certain complex function, such that this function, this particular function, is obtained in the way of this substitute. This one. So this is equal to z plus z, maybe write it down like 1 over z divided by 2, and this will be sine of t is equal z minus 1 over z divided by 2i, and those are the substitutions for the trigonometric functions, and since we have here z is equal e to it, we can derive that dz is equal I e it dt, which gives me that dt is equal to dz divided by iz. Yes, notice that's exactly z. And we get the third equation. In such a case, we obtain that this integral I, which is exactly from 0 to 2 pi, of the function r cosine of t sine t dt is actually nothing else than the complex integral. It is just exactly complex integral, and this is on the unit circle of this function r, and that will be cosine t. This cosine t is replaced by z plus 1 over z divided by 2, z minus 1 over z divided by 2i, and that one is dz divided by iz, and we get the conversion. This is conversion to complex integral. And now let's denote this particular function is my f of z function. So we can write now the answer to this problem. The answer will be 2 pi I, and then we have here that this will be sum of the residues of this function f of z at the point zk, and here zk must be inside the unit circle. So you can, let's make a picture. So we are obtaining, this is the unit circle. That's the 0, and then that one is the coordinate system. This one is 1. And there are certain singularities inside and certain singularities outside, but those outside are not important, only inside. So inside place, and outside does not participate in this computation. So those are from the inside. And that's what we have to pay attention to. And let's do the examples and let's see how it works in the practice. Example number 1. So just simply compute, and my integral is just simply integral from 0 to 2 pi, and here I have here dt, and here I have here 1 minus a, 2a cosine of t plus a square, where 0 smaller than a smaller than 1, and we can immediately apply the conversion. So let's say like this, conversion to complex integral. And it goes like this. So let's say our integral is equal, and then integral over the from 0 to 2 pi becomes integral over the unit circle. Then dt becomes dz. And we do not forget there will be also iz. And then what is inside is, let's say, copy. So we are getting here, where is the integral? Okay, 1. So 1 is 1. And then minus 2a, and cosine is equal z plus 1 over z divided by 2, and then here is a plus a square, close it, and remember this is this part, This is exactly your dt. So it has to be never forgotten, iz that is there. And then do some simplification, 2 cancels, and we are getting the following integral. So this is integral over the unit circle, and then we have here d. I put here I outside for convenience, and then I have here dz, and here we are getting minus az squared, and this is plus, and that one is a squared plus 1, z minus a. This is a quadratic polynomial. It can be factorized relatively easily. You can check it if you want. I will just simply apply this factorization. You can always practice more using your this as a kind of a yeah. So when you practice, you can check this factorization. I have this factorization, and then immediately we get the 2 simple pole. One is equal to a, and the second simple pole is equal to 1 over a. And you can see that this one is inside of C, and that one is outside of C. So that means that only Z0 participates in these computations. So let me write it down. Now you can go here and write it down. This one is equal. This one is equal 2 pi I, and now don't forget this 1 over I that we took out, and then we put here a residue of this function. So this is 1 minus a z minus a, and this is at the point A, and the point A, not 1 over A. It's kind of a at the point A. Yes, better. So we do the simplification here, cancel this I, and compute the residue. So residue is easy because that's a simple pole. Simple pole, put it here, simple. So that one is equal to pi, and the residue you are getting here, this is 1 divided by 1 minus a, and we replace z by a, so that what is obtained, and this gives me 2 pi 1 minus a squared, and the integral is computed. So example number 2. And in the second example, I chose a different type of the function. So just to make sure, we have here a situation in which we can see all kinds of the possible cases. So in this case, I have that function. So that one, AB, and this one is again cosine of t squared. I'm sorry, I should maybe get an example with sine, but that one probably will be done on the exam. So it's sine. So I have that one where we have here 0 smaller than b smaller than a, and let's do the computation. So first we start with the conversion. So we have here the conversion that goes like that. So this integral, maybe integral, which is that one, I'm converting to the complex interval over the unit circle. So this becomes immediately, so dt becomes dz, and maybe I should make a long line. And here we have here already I and z standing here. Now we have this bracket that has a plus b, and this one is equal to z plus 1 over z. Maybe let's say, let's make it more z plus 1 over z over 2 square, and now I and z. Yes, so maybe better organized now. We have always better organizing. So do the simplification. So of course I take this 1 over I outside, it will be helpful, and then I do some simplification inside, so maybe put everything on the common denominator inside. So this is my dz, and I have here the common denominator is 2z. Yeah, this is 2z. So this is 2z, so this is 2az, and then you have here plus bz square plus 1, b becomes b square, and here we have here I z. I can go and simplify that one. So this is, so maybe write it down like this, 4 divided by I, and this is c, and here we are getting here z dz, and here we have a quadratic polynomial which is b z square plus 2a z plus b, and that one is square. Notice that this polynomial, this has two roots. This bz square can be easily solved because that's easy to do the polynomial. You can use the completion to the full square, and you can find out that we have here two roots. So first one is equal to, so put it like this, z1 is equal to minus a, and this is plus, and here we have here a square minus b square divided by b, and the z2 root will be equal, and this is minus a minus square root of a square minus b square over b. So I will have here two singular points, except we have to check which of them is inside the circle, unit circle, and immediately recognize, notice that I put here absolute value of z2, so this will be nothing else than a divided by b, and this will be plus, and this will be square root of a square plus b square minus 1, and we can see that the a is larger than b, so that one is larger than 1, and of course in such a case we are getting here that that root is larger than 1, so we can write it down that z2 is outside C. So now there is a z1. Let's check the z1, and z1 can be, let's say, you can verify that this is inside, you can verify that this one is inside, but I would say just try it. So maybe like this, verify, okay, verify that now that z1, and now I can write it down what is exactly, oh, second, what's happening? I lost the track. Oh, z1. So this one is equal to a, this is equal to a minus square root of a square minus b square divided by b, that one is indeed smaller than 1. And you just do it as follows. So that means this is equivalent to a minus square root of a square minus b square smaller than b, and that one is equivalent to a square minus b square larger than a minus b, and that one is a square minus b square is larger than a square minus 2ab plus b square, and that one gives you cancel something, so this cancel, and you are getting here that 2ab is larger than 2b squared, which is actually assumptions that a is larger than b. So yes, indeed, yes, 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 it is. So in such a case, we can return to our integral, and we have here z1, which is the good root. So let me write it down. Solution, final step is that your integral I, which is equal, this is 2 pi I, and now remember we have here the integral, this integral, so this is 4i, so this is equal 4i, and maybe I take it out, yes, times 4i, and I have here a residue of the function, and my function is here, so this is z divided by, and here is the factorization of this function, so this will be b squared, and this is z minus z1 square, z minus z2 square at the point z1. So this is at the point z1. So now let me do some cancellation, and then you are getting here, this is equal 8 pi, and this residue, this is, unfortunately, that's a pole of order 2, because we have here the power 2, so this is, and this is pole of order 2. Why it is 2? Again, look, there is the power here 2, so that means it's a singularity of appearing as a 0 in the denominator with the power 2, so that means pole of order 2. So I need to compute the, multiplied by that value, I need to compute the derivative, and this is z. Here we have here b squared, and that one is z minus z2 square at the point z is equal z1. Continue, this is equal a pi. Take the derivative, so here we have here derivative of the first one is 1. Maybe take this b square here, and then I have here z minus z2 square, and then you have here minus, because that's a negative power, and this will be 2z divided by z minus z2, and that one will be cubed. And here put z is equal to z1, which can be simplified. Now let's do the simple. 8 pi b squared, and here we are getting here, this one is z1 minus z2 square 1, and this is minus 2z1, and that one is equal z1 minus z2 cube. I want to simplify it more. I will put it like this. This is 2 pi b squared. Put everything over a common denominator, 1 minus z2 cube, and then you have here z1 minus z2, and this is minus 2z1. Very good. And then I'm getting here, this is equal to 2 pi divided by b squared, and here I'm getting minus, and this is z1 plus z2, and here I have here z1 minus z2 cube. Let me check what is z1 minus z1 plus z2. So where am I? Where am I? Oh, z1 plus z2. Let's write it down. z1 plus z2 is equal to is equal minus, this is equal minus 2a over b, and z1 minus z2 is equal, one moment, I have to separate it, so this one is equal to positive. So this will be 2 square root of a squared minus b squared divided by b. Go back, so I can rewrite it down. So this is equal, I'm getting here 2 pi, and that one is equal to a over b. So this is 2a over b, and that one is b squared, and that one is equals a squared minus b squared. Did I put here 2? Yes, there is a 2, so there is a 2 divided by b to the power cube, and do the simplification, so I'm getting here, this will be, yes, I just detected what is usually happening, transformation. This was 8, so still 8. This was 8, so that must be still 8. So this is my 8, and I got it right in time. So I'm getting here 16. This one is equal to 16, A. This is A. And now B, and this is B cubed. All cancel, so there is nothing. And then you have here 2 to the power 3. And where is pi? Pi is here. And then you have here square root of a squared minus b squared cube, put it here. So now, what is the 16? So this is 4 times 2 is 8, so this is equal to 2a pi divided by, write it down like this, a squared minus b squared by 3 over 2. Now let me check it. Probably, yes, we got the answer correctly. So that's the answer. So we achieved the goal. Yes. So try to compute these integrals without using residues. So maybe let's switch another paper, and maybe let's say I need more paper, probably for the upcoming let's say examples. So we have here another one, and let's write it down. Type 2. And this one will be rational functions. So this integral of improper integrals. Improper integral of rational functions. Improper integrals of rational functions. So in this case, so what is my integral? So this integral will look like that. So this will be integral from minus infinity to infinity, and my rational function will be just simply a polynomial over a polynomial. So you have two polynomials, dx. So this means a, p, and q are polynomials. And in this case, we also need to assume the following assumption, that q of x, that means for the real numbers, is never equal to 0. That means for every x belonging to R. So that means it's a kind of a even degree polynomial that never gives you 0, like quadratic polynomial with the negative discriminant. So in such a case we have here we have no roots, so that means, so that's this one. And the third assumption, C, is that the degree of q as a polynomial is larger than degree of p plus 1. So that means the difference between the degree of numerator and denominator is 2. That means the numerator has the degree at least 2 smaller than the degree of the denominator, and that will guarantee the convergence of this improper integral. So with these assumptions, this integral will converge. On the other hand, put it like this. Notice that the function that let's say like this, that the integral, maybe like this, the assumption C guarantees the convergence of the integral I, the improper integral I. So it is actually convergent, that means that it's a number. And we also have, and in this case we have that the limit as z goes to infinity, yes, 1 second, z goes to the infinity, and maybe I put it like this, maybe write it down like that. So I just simply, we also have 4, and I put here f of z, this is my complex function. Now p of z, I replace variable, real variable by complex variable, so we have also, that one, and let me find it, move the page, so this will be limit as z, a modulus goes to infinity, and then you have here z, and this will be f of z is equal to 0. Notice, that's important. Why? Because in such a case, if you write it down, so let me write it down, this will be z p of z. So if this is the degree, so the degree of z p of z is strictly smaller than degree of q of z by the assumption, because that one gives you 1 plus degree of p, and you see immediately that if the degree of the numerator is larger than the degree of the denominator, if the degree of the denominator is larger than the degree of numerator, then in such a case the limit must be 0. So that condition will be also satisfied, and we emphasize, look, we put it in red, so this is the condition that follows from C. So C implies this particular condition. So now let's do the following. So we will apply the method. So put here, our method is this one. Method. So first of all, I look at the coordinate system. So my coordinate system, let's say like this, I need to make sure that everything fits correctly. So this is my x-axis, this is my y-axis. And now, here we have singular points. What are the singular points? Singular points. Of f of z. This is f of z. So that means, what is our f of z? One more time. My f of z is here. This is my f of z. So what my singular points are? Polynomials are entire functions, so that means simply r. So r zeros of q of z. Zeros of q, that means we solve the equation equals 0. And we have a roots. And of course these roots will appear in pairs, like that point and conjugate, that point, this point and this point, and maybe that point and maybe that point. Maybe too many? Maybe. So maybe make it lower. I just don't want it to go too far. And that point. So you have the roots. So those are the roots of the denominator. Those are singular points. and they're all poles, and an order of such a pole is exactly the multiplicity of the zero. So what kind of a root? If it's the root of multiplicity 1 or higher, and that's exactly will be translated into the order of the pole. So now what I'm going to do is, I'm going to look at this particular picture, but I'm going to concentrate on the portion of the, that means I'm going to totally ignore everything what is okay, what is here. I'm going to ignore this picture. We don't even talk about it. And then I'm going to work on the upper half plane. Namely, I choose semicircle, put it like this. I choose the number r large enough such that this semicircle that goes all about like that. Too much. Okay, sorry. I start smaller. Semicircle. And this semicircle, they denoted by color, and then of course it goes here minus r, and I'm getting here another one, that one, and I return on the real line to the point r, and this semicircle and this segment on the real line contain all the singular points in the upper plane, all upper plane, in upper plane. Upper plane, all singularities, all singularities in the upper plane. So this are here. So now I say, okay, I have here this function f of z, so I can check it out. What do I have? So let me write it down. I'm looking at this integral, so my integral is actually this integral, and I call this contour CR. So what is the contour CR exactly? CR will be equal, and this will be KR and union, and this minus R and R, segment, and this will be segment, this on the real line. So this will be, how to delete it? This is CR, very good, and then let me do it, equal, sorry, dr, so so put it like this, f z dz, no, sorry, something, okay, f z dz. This integral will be translated into one integral is kr f of z dz, and that one is plus, and there is a surprise. This is from minus r to r, which is this segment on the real axis, and this is everything the same as in the case of the line integral. Just remember, line integral on the real axis is exactly the real integral. So that means, what do I get here? I'm just getting here, this is my f of x. I can actually write it down. This will be my, okay, f of x, sorry, and I make sure that this will be f of x dx, and one more time, f of z is equal p of z divided by q of z. So keep it in mind. So now, okay, so what happens? So if I take the different circle, so I take, for example, a larger circle. Okay, let's go take a larger circle. I take another circle, like here, bigger circle. So I put here number like this is r. I put here capital R, and I can take big circle. Did I miss anything? Yeah. I take this circle, and then I take that integral. So this is my contour CR. So you look at the the area, let's say the region between these two contours, so the region here is that one. This is the region between these two contours. There are no singularities here, no singularities. And that means by the Goursat theorem, that one will be always equal to the CR larger circle of f of z dz will be always, this will be always true. So that means this integral doesn't really depend for sufficiently large, of course, radius of the size of this semicircle. The important thing is that this semicircle contains all the singular points. And in such a case, we can basically write the answer. The answer will be 2 pi I, and then you can write it down, sigma, and this will be all the points belonging to the upper plane. So I put it like this. This is singularities, and I put here imaginary part of zk must be positive, and this will be residue of this function f of z at the point zk. Very nice. I got that value, so I know doesn't matter what is the radius r, or small or big. It will be the same value. It will be the 2 pi I sum of residues. But what happens to the other side? So let me write it down. What do we got? We got actually the following situation. We got the 2 pi I, the sum of the residue of the upper plane of the, those are the residues, z, and this is zk, is equal, and that one is equal for every r. So this is for every r larger, sufficiently large. So this will be integral over kr, and this is f of z dz, and this is plus of r from minus r to r, and this will be f of x dx. But now, look, this integral, what will happen if I take limit with r going to infinity, of this integral over kr f z, and this one is dz. So let's write it down. This will be the same as limit. This will be r to the infinity. And now I can say, I can rewrite it down. Like that. I put here maximum of f of z for z is equal to r, and then pull it out, and then I write it down. This is kr, and that will be dz, and then I'm getting here, this is limit, and this one is r going to infinity, and then I'm having here 2 pi, and then I have here r, so maximum z is equal to r, and that will be, okay, this will be like a z f of z, and then you remember, we have this conclusion that we concluded here, that this limit is 0. This limit is 0. So actually, you see here, this maybe it's appropriate to write it down r, which is r is of course equal to z. So this is r, so it must be equal to 0. So if you write this limit, then I'm getting from the previous one that the integral standing here, this integral goes to 0 as r goes to infinity, and this goes to the minus infinity f of x dx, and we derive the formula, and we obtain that the integral, write it down, from minus infinity infinity, and this will be px qx, that's my f of x, dx, is equal to pi I, and that one is sum, and this over all zk, such that imaginary part of zk is larger than 0, and then you have residue of the pz, that's my function f of z, this is my q of z at the point zk. And that's the formula for the computations of the integrals. So this is for type 2. So we have the formula for this integrals. Of course, what's supposed to happen now? I'm supposed to do an example, at least one or two examples. So let's start maybe with kind of, okay, let's do example. Let's do example that would look impossible without residues, because yeah, the idea is that if you don't know the residues, try to solve this integral. So the example number 3. Example number 3. So compute, and you are supposed to compute this integral. So now I put it like this: integral is equal, and this is from minus infinity to infinity. Maybe write it down like this, from 0 to infinity, because we want this to be in a certain way like a 1 plus x squared to the power n, where n is arbitrary natural number n. Okay, try to integrate this integral without, try to find the value of this integral without the method that I have explained to you above. So let's do it, and let's show what it is equal to. So interestingly, you can notice immediately that it satisfies all the properties above, except you have to write it down that your integral has to be written as a 1/2 of the integral that we were considering above. So the theory is applicable. This is an even function, so of course it will work, to the power n. And now you look at that one and you say, yes, I have here the formula. So I remember I write it down 1/2, and now I have to look at the, so maybe I remove it here and put here margin, and I have here x squared plus 1 is, so put it like this maybe, z squared plus 1 is equal to z minus I, and this is z plus I, and since the I, so that means we have 2, z0 is equal to I, z1 is equal, z1 is equal to minus I, so this is in the upper plane, so it's good, and that one we disregard. So that's the only root that is playing here. So we have here one singularity, so we can definitely go here and continue. So that integral will be equal, and we write it down 1/2, and now 2 pi I, like it is in the formula, you have here 2 pi I, and there is only one residue, so put it like this, residue of the function 1, and this is 1 plus z squared to the power n, and here at the point I. So this would be the answer. This is the answer. So what is the task? We need to compute this residue. So now you can write it down, since the function f of z, this is our function, which is equal 1 over, z squared plus 1 to the power n is the same as 1 divided by z minus I to the power n, and this is z plus I to the power n. So z0 is equal to I is a pole of order of order, what? N. N, because that's the power n. So this is the order of that pole, n, n. So in such a case, if you would like to compute the residue, so put it like this, the residue, and put here f of z at the point I will be equal, and you have to understand this is n, so this will be 1 divided, and again n minus 1 factorial, and then you take the derivative of order n minus 1, n minus 1, and now of that expression, and we learned it before, so I do not go into the too many details, and this is z is equal to I. So let's compute this derivative. So let's start with the first derivative. So what do I get here? Maybe let's write it down. The n. So what is the derivative? Kth. Kth derivative dzk. So you understand this is the same as this function. So our function is here is 1. So put it like this. This is z minus I to the power n. So of course that implies that this is z. Okay, maybe put it here. Z plus I to the power minus n, so I don't need this, will be equal, so you take the first derivative, so this is minus n, and then the power in minus 1, minus 2, minus 3, so if you want to do minus n, then this will be minus, so this will be minus k plus 1, and this will be z plus I, and this is minus n minus k plus 2. Sorry, so I need to erase this thing. I'm already. Yes. Okay. K of z plus I to the power minus n. So first derivative, second derivative. So what happens? The power is increasing. So this is minus 1. And then you go, then you take the third one. So this is the third one. So what is this? This means this is equal to minus n, and this is minus k plus 1. And what will be here? So this will be z plus I, and this will be to the power minus n, and this will be minus n, and then will be minus k, and that will be minus k. Yeah, minus k. So, okay, so I have it. So this is d n minus 1, d z n minus 1, and I put here z plus I minus n at the value z is equal to I. I'm getting here that this one is equal to minus 1 to the power n minus 1. There are n minus 1. There are exactly n minus 1 factors here. So there are n minus 1 factors, and then you can put it here, the product. So what is the product? So this will be like n times n minus 1, blah, blah, blah. Sorry, n plus 1, and then you have here n to n. So take k is equal to n minus 1, so this will be 2n minus 2. Yeah, and in the bottom I have here z0, so this will be 2i, and this will be there will be n 2n plus 1. So this is 2n minus 1. Minus 1. So I'm getting here, this will be 2n minus 1. Minus 1. And we have the computations. Maybe simplify. Minus 1 to the power n minus 1. This will be, this will be, oh, I write it down like this. 2n minus 2 factorial divided by n minus 1 factorial. This will be 2 to the power 2n minus 1. I to the power 2 is minus 1. So I can write it down. This is minus 1 to the power n. And minus I, and I can put here at the top. So I get here that this and that gives me minus 1. So this is equal to the minus 1. And then I have here I. And then I have here divided by n minus 1 factorial. 2 to the power n minus 2 factorial. 2 to the power 2n minus 1. Wow, so this one, okay, I can write the answer. I can the integral is equal, let me write it down. So this was pi I. Here we have a simplification. So this is pi I. Let's write it down. Pi I times the residue, which is this one, minus 1 I 2n minus 2 factorial. And this one is divided by n minus 1 factorial, 2 to the power 2n minus 1. Now I see this, and this is just 1. Because I times I is minus 1 times 1 minus 1 is 1. Okay. So I have the answer. So the answer is pi, and here we have 2n minus 2 factorial divided by 2 to the power 2n minus 1. 2 to the power minus 1. So this would be the example number 3. So example number 4, just a simple one, I hope. A simple one is the following: compute, and we have here integral. Let me put it like this. Okay, I put here integral from minus infinity to infinity. I put here x dx, and here I have here x square plus 4x plus 13 square. So we know how to compute it. So first try to find the singular points, and let's do it so you can solve it easily. So you are getting here that you have two singular points, z1, z2, which is equal. So this is plus, so it will be minus 2, and this will be plus minus 3i. Check it. You just do the simple computation by yourself. So there are two roots. Only one of them is in the upper plane. Namely, look, this is the minus 2, and this is 3. So we have here that root is here. So this is minus 2 plus 3i, and the other one is in here. So this is the disregarded part. So the only one is that one. So I put it like this: z0 is equal minus 2 plus 3i, And then, of course, you can rewrite the integral using this formula. So let me write it down. So this integral, I put it here, integral is equal, and this is minus infinity. So maybe put it like this over. So this is integral. Okay, just write 2 pi I, and this will be residue. Just write the formula. You don't need to do. And then x is z, so this will be z. This will be z squared plus 4z plus 13 squared, and at the point minus 2 plus 3i. So let's compute this residue. So residue, so here the residue of this function, so I can rewrite this function, and I know how to write it. This will be z minus 2 minus 3i squared, and this will be z minus 2 plus 3i squared at the point minus 2 plus 3i. So that's the pole of order 2, because you have here the exponent 2 pole. So therefore I will have the formula. So this will be equal, and this will be again d dz, and you have here that one, z divided by z minus 2 plus 3i squared, taken at z is equal minus 2 plus 3i. Minus 2 plus 3i. Just checking. Yes. Yes, except it's plus. Yes, I knew. This is plus. This one is plus, because that's minus, so this must be plus. And this one is correct. This one is correct. This is plus. Okay. So let's continue. So the derivative. So we are getting here. This is z plus 2 plus 3i, and that one is minus z, and that one will be 2, and divided by the derivative of that one. So this will be z plus 2 plus 3i to the power 3. Take it, so z is equal minus 2 plus 3i. So let me check it again. And that one gives me z1. How much it is z1? z1 plus, so this is equal minus 2 cancels. I'm getting 6i. This is 6i minus 2. So I'm getting here minus 2 times minus 2 plus 3i, and then divided by, and here we have similar situation. So what do I get here? I'm getting this cancel. We are getting here 6i to the power 3, and that one is equal, 6i cancels. Yes, this and this cancels. So I'm getting here 4. This is 4. And here I'm getting minus 6 to the power 3i. Okay, let's plug it in. So I'm getting the answer I, our integral. This is the answer. Answer is equal. So let me go back and let me check. This is 2 pi I and the residue. And the residue is that one, 4. and this is minus 63i. Do the simplification, this and that, simplify. Maybe you notice this is 8, and maybe you notice that this is 2 to the power 3, and this is 3 to the power 3, and here pi. So 2 to the power 3 is 8, so it cancels, and then we are getting here 27 minus pi divided by 27, and we computed the integral. So we computed this integral, so the, let's say like this, that concludes this example, and then this part of the class of lecture is over. Thank you.